Earth's dynamic structure and plate movement. Rather than embarking on distant cosmic journeys to explore far-off horizons today, our focus turns inward to our own planet, examining Earth's geological past, its current state, and future transformations. Our investigation centers on the fascinating and complex phenomenon known as plate tectonics, specifically exploring the fundamental forces and mechanisms that control the shaping of Earth's surface features, while addressing the crucial question of continental movement directions in contemporary times. However, before delving into these modern concepts, we must first establish the historical foundation. Our planet's surface displays a remarkable configuration of vast oceanic basins and continental landmasses. Across these regions stretch immense mountain chains, profound oceanic trenches, and expansive valleys. These surface features represent clear evidence of dynamic tectonic and volcanic processes that continue to shape our world. To gain deeper insight into these phenomena, we must examine Earth's internal architecture and understand the processes occurring within its depths. Unfortunately, current technological limitations prevent direct exploration of Earth's interior structure, particularly for human observation. The deepest mining operation currently reaches only 4 kilometers into the Earth's crust. Meanwhile, the most profound drilling achievement remains the Kola super-deep borehole, located on Russia's Kola Peninsula. This remarkable vertical drilling project achieved a depth of 12,262 meters. To put this achievement in perspective, continental crustal thickness typically ranges between 30 and 40 kilometers. Despite these limitations, scientists have successfully gathered substantial knowledge about our planet's deep interior. This understanding has been developed primarily through geophysical investigation techniques, with seismic wave analysis forming the cornerstone of these methods. These studies involve measuring vibrations generated during natural earthquakes or controlled explosive detonations within Earth's subsurface. Materials of varying density and composition transmit seismic waves at characteristic velocities, enabling researchers using sophisticated monitoring equipment to measure these speeds and analyze the resulting data patterns. Additional geological investigation methods complement seismic studies, including direct drilling operations and comprehensive geological mapping. Scientists also examine xenoliths, foreign rock fragments that reach the surface during volcanic eruptions, and analyze meteorite samples, since hypotheses suggest Earth's core composition resembles that of iron meteorites. These combined research efforts have revealed that our planet possesses a distinct layered architecture composed of multiple concentric shells. The outermost layer, Earth's crust, represents the thinnest shell, while the mantle constitutes the most voluminous component, comprising approximately 70 to 80% of the planet's total mass. The mantle consists of solid material with lower density compared to core material. Temperature and pressure conditions increase progressively with greater mantle depth. Within the mantle exists a partially molten zone that facilitates the movement of solid materials toward Earth's center. At the planet's heart lies the core itself, representing roughly 30% of total planetary mass. The solid inner core exists within a liquid outer layer, generating our planet's magnetic field through this configuration. For our current discussion, the lithosphere demands primary attention, Earth's rigid outer shell comprising both the crust and the uppermost solid mantle portion, extending down to the asthenosphere. The asthenosphere represents a plastic, deformable layer that permits lithospheric plates to move across its surface. Notably, Earth's entire surface consists of these lithospheric plates, which can be visualized as enormous shell segments on a planetary scale organism. The largest plates include the Pacific, North American, South American, Eurasian, African, Antarctic, and Australian plates, along with numerous smaller plate systems. All terrestrial topographic features and continental positioning result directly from lithospheric plate movement. Throughout history, researchers and philosophers from ancient Greek and Eastern civilizations pondered questions about Earth's surface formation and proposed various theories. Medieval scientific thought was dominated by the contraction theory, which attributed mountain formation to planetary cooling and subsequent compression. However, this explanation proved inadequate. The closest approach to accurate understanding came in the early 20th century through German geophysicist and meteorologist Alfred Wegener, who proposed that approximately 200 million years ago, all continental masses were unified into a single massive supercontinent, which he termed Pangaea. This supercontinent comprised two major components, northern Laurasia and southern Gondwana, surrounded by the Tethys Ocean. Wegener's continental drift theory was founded on the remarkable similarity between the coastlines of Africa and South America, which appeared to fit together like puzzle pieces when positioned appropriately. The continental drift concept gained renewed momentum and development during the late 1950s, thanks to advances in geophysical Earth studies and aerospace research capabilities. These technological improvements enabled scientists to examine vast geographical areas for the first time and identify patterns in mountain belt structures, fault systems, and other geological formations. Ocean floor research represented an even more significant and transformative development. Scientists discovered the existence of a global network of mid-oceanic ridge systems, rift valleys, fault zones, deep trenches, volcanic structures, and related geological features. These investigations revealed that ocean basins experience active tectonic processes and demonstrated that oceanic crust is considerably younger than continental rock formations. While the most ancient continental shield rocks date to approximately 3.5 billion years, the oldest oceanic floor rocks are merely 170 million years old. Research also established a clear pattern showing that oceanic crust age increases with distance from continental margins. This evidence led to the development of modern plate tectonic theory, explaining continental movement. The data revealed that continents gradually migrate away from mid-oceanic ridge systems, while new magmatic material emerges at these locations, forming contemporary ocean basins. Plate movement theory gained additional confirmation when seismic activity mapping became possible. This analysis demonstrated that earthquake occurrences don't represent random surface phenomena, but instead follow narrow, elongated zones that frequently correspond with anomalous topographic features such as mountain belts and deep trenches. These zones mark the boundaries where tectonic plates interact. Plate boundary interactions display various characteristics, and current scientific understanding recognizes three distinct types. The first type, divergence, occurs when plates separate from each other at their boundaries, resulting in the formation of deep fractures or rift systems. Notable examples include the Baikal Rift and the East African Rift System, which extends thousands of kilometers. During lithospheric stretching, the crust becomes thinner while molten mantle material rises upward. Thermal expansion effects create topographic elevation and plateau formation. In simplified terms, this process increases Earth's surface area. However, if surface area increases in some locations, compensating zones must exist where continental surface area decreases. This occurs when oceanic plates collide with continental plates. For instance, the Pacific Plate moves northwestward at approximately 8 centimeters annually and encounters the continental Eurasian Plate, which possesses greater structural strength and lower density. Consequently, the thinner and denser oceanic plate descends beneath the continental plate. This collision process is called subduction and represents the second type of plate movement associated with convergent boundaries. Oceanic crust absorption compensates for new crust creation at mid-oceanic ridges. These subduction zones host extraordinarily complex interactions between crustal and mantle materials. Oceanic crust can drag continental crustal blocks into the mantle, where they melt and, due to their lower density, return to the surface. This process created volcanic systems on Earth. When two oceanic plates collide, one plate slides beneath the other, similar to overlapping elements, forming a subduction zone above which island arc systems develop. Continental plate collisions result in collision zones, creating powerful folded mountain regions like the Himalayas. The entire alpine Himalayan mountain belt essentially represents wrinkles on our aging planet's surface. These features result from Africa's northeastward movement at nearly 2 centimeters per year, India's northeastward motion at 5 centimeters per year, and Arabia's northeastward movement at 2 to 7 centimeters annually. The differential rates of these movements created the Red Sea, which continues expanding at approximately 1 meter per century. Research indicates a different fate awaits the Mediterranean Sea, complete disappearance within roughly 50 million years. Africa's continued movement toward Europe will replace the sea with a mountain belt comparable in size to the Himalayas, creating a truly transformed world. The third type of plate movement involves transform faults, where plates move parallel to each other at different velocities. In oceanic regions, transform faults extend perpendicular to mid-oceanic ridges, segmenting them into sections averaging 400 kilometers in width. Active transform fault sections exist between ridge segments, where earthquakes and mountain-building processes frequently occur. These fault zones often expose mantle rocks at the surface. Transform boundaries on continental surfaces are relatively uncommon. The San Andreas fault system represents perhaps the only currently active example of this boundary type, separating the North American and Pacific plates across 1,300 kilometers, one of Earth's most seismically active regions. Annual relative plate movement measures approximately half a centimeter, with earthquakes exceeding magnitude 6 occurring on average every 22 years. Advances in geological disciplines, including geodynamics, lithospheric plate kinematics, and satellite geodesy, enable both future Earth predictions and historical reconstructions. These reconstructions allow scientists to model past geodynamic conditions and identify patterns in global environmental changes. Examining Earth's configuration 300 million years ago at the end of the Paleozoic era reveals a single supercontinent called Pangaea. This unified landmass consisted of several large continental blocks connected by mountain systems, stretching meridionally from polar latitudes to equatorial regions. Pangaea thus traversed all of Earth's climatic zones and, at the end of its existence, separated into northern and southern continents, Laurasia and Gondwana. Modern Eurasia and North America originated from Laurasia, while Africa, South America, India, Australia, and Antarctica descended from Gondwana. Currently, continents exist at nearly maximum separation stages, along with human populations distributed across these landmasses. Regarding Earth's future configuration, several theories exist about continued lithospheric plate movement, but ultimately all these theories predict the formation of another supercontinent, variously named Amasia, Pangaea Ultima, or Pangaea Proxima. This reunification is projected to occur within approximately 250 million years, by which time humanity's condition will likely be significantly altered. This cyclical pattern of continental breakup and reunification represents not coincidence, but a regular geological process. Current science cannot fully explain this phenomenon, but attributes it with high probability to deep Earth processes, specifically the evolution of lower mantle structures. Notably, similar supercontinent formation has occurred at least 5 times in Earth's history, with each supercontinental cycle lasting 600 to 600 million years. When all terrestrial landmasses and continental crustal blocks unite, Earth hosts only one enormous continent and one vast ocean. Subsequently, rift genesis begins as the supercontinent fractures into multiple continental lithospheric plates, which internal forces then disperse across Earth's surface until they eventually reassemble. Whether humanity will witness the next supercontinent formation remains debatable. However, such an event would necessitate confronting radical climate changes. If land masses accumulate at planetary poles, ice formation and persistence would occur more readily, making global cooling periods truly extreme. Some opinions suggest that any supercontinent appearance triggers radical climate change, which seems logical since a single enormous landmass would completely restructure oceanic circulation patterns, leading to global heat flow redistribution. We must remember that oceanic crust subduction sustains volcanic activity. Supercontinent formation essentially eliminates this phenomenon. Regardless of our negative perceptions of volcanic eruptions, they reportedly help maintain stable planetary climate. It's probably not coincidental that both the hottest and coldest periods in the past 350 million years occurred during Pangaea's existence. Future Earth will differ completely from our current understanding. Predicting continental movement requires knowledge of how mantle convection affects crustal dynamics and how subduction influences mantle processes. This information will improve understanding of earthquake and volcanic phenomena. Ocean currents, greenhouse gases, and ice coverage are all directly connected to Earth's geology and deserve thorough investigation. Whatever form the next supercontinent takes, it will bear no resemblance to the boundaries that humans meticulously draw on maps while waging wars over these territories. Natural forces ultimately prove far more powerful, having long demonstrated their supremacy beyond human control. Earth's unique climate system and El Niño dynamics. Our planet's climate system stands unique among known worlds. No other planet has been discovered with climatic conditions comparable to Earth's. Furthermore, Earth's climate demonstrates constant variability. It remains dynamic and changeable. These variations stem from both human activities and, significantly, solar energy input and energy exchanges between different components of the climate system. Solar radiation propagates through space as electromagnetic energy, termed solar or shortwave radiation, reaching Earth regardless of orbital position or seasonal timing. However, the climate system doesn't utilize all intercepted energy. Portions return to space through various reflection mechanisms, primarily involving cloud systems and Earth's surface. Atmospheric absorption doesn't capture all radiation, allowing some to reach the surface, which then heats up and emits characteristic long-wave radiation. Most of the surface emission gets absorbed by the atmosphere, which subsequently re-radiates energy either groundward or spaceward, ultimately returning energy to space. Globally averaged, Earth maintains overall energy balance, though not uniformly across all regions or time periods. Nature's inherent complexity and beauty occasionally present humanity with numerous climate puzzles, including climate variations associated with the El Niño phenomenon, one of the most intriguing factors influencing global weather patterns. El Niño represents a climate pattern describing unusual surface water warming in the eastern tropical Pacific Ocean. La Niña, the corresponding cold phase, describes unusual surface water cooling in the same region. Contemporary technology gathers data about this phenomenon using various instruments. For example, the National Oceanic and Atmospheric Administration operates extensive scientific buoy networks. These buoys monitor ocean and atmospheric temperatures, current patterns, wind conditions, and humidity levels. Approximately 70 buoy stations are positioned throughout the southern Pacific Ocean. These crucial instruments transmit data to researchers and meteorologists worldwide. Utilizing this information alongside satellite imagery, scientists can more accurately forecast El Niño events and visualize their development and global impacts. This phenomenon influences ocean temperatures, oceanic current velocity and intensity, coastal fisheries, and regional weather patterns from Australia to South America. El Niño events occur irregularly at 2 to 7 year intervals. However, this phenomenon lacks the predictability characteristic of, for instance, oceanic tidal cycles. Understanding this phenomenon's development requires knowledge of normal Pacific Ocean conditions unrelated to El Niño events. Typically, strong trade winds blow westward across the tropical Pacific zone, driving warm surface waters toward the western Pacific, where they encounter Asia and Australia. Due to these warm trade winds, surface waters typically measured 0.5 meters higher and 7 degrees Celsius warmer near Indonesia compared to Ecuador. Westward warm water movement causes colder water upwelling along the coasts of Ecuador, Peru, and Chile. This upwelling process, the rise of deep oceanic waters to the surface, also affects global climate patterns. Warm water temperatures in the western Pacific promote increased precipitation around Indonesian and New Guinea islands, while trade winds maintain their normal patterns. During El Niño events, westward trade winds weaken along the equator. These atmospheric pressure and wind speed changes cause warm surface waters to move eastward along the equator from the western Pacific toward the northern South American coast. These warm surface waters deepen the thermocline, the oceanic depth boundary separating warm surface water from colder depths. During El Niño, thermoclines can descend to 150 to 200-meter depths. This thick warm water layer prevents normal upwelling processes. Without nutrient-rich cold water influx, eastern Pacific zones cannot sustain their typical productive coastal ecosystems, causing fish populations to die or migrate. Currently, the World Meteorological Organization has announced that the relatively cool climate phase has concluded, with a warm period approaching that will bring severe drought to some regions while causing extreme precipitation and flooding in others. Annual reports document fundamental climate parameters including average annual temperatures, atmospheric pressure, precipitation amounts, and phase states of major oceanic processes affecting planetary climate. The 2023 report indicates that the cold La Niña phase ended mid-year, associated with southern oscillation phenomena in the equatorial Pacific. This particular episode lasted abnormally long, 3.5 years rather than the typical 1 to 2 years. Scientists believe that energy accumulated in the global climate system, previously constrained by La Niña mechanisms, may release onto the planet with unpredictable intensity during 2024 and 2025. The previous temperature record occurred in 2016, also during an El Niño phase. Possibilities exist for surpassing this record in 2024. Climatologists project that the coming 5 years have a 66% probability of becoming the warmest in meteorological observation history. Researchers forecast record heat globally, but primarily in tropical zones between 30th parallels north and south, where over 1/3 of the planet's population resides. Projections indicate that average temperature increases of 2.7 degrees by centuries and represent realistic scenarios, though worse possibilities cannot be excluded, with temperatures potentially rising to 4 degrees. In such cases, up to 50% of the planet's population would find themselves outside favorable climate niches, potentially triggering large-scale Earth surface transformations and fundamentally altering our planet's life-supporting capacity. El Niño and other natural phenomena repeatedly demonstrate nature's fascinating and occasionally dangerous power, significantly impacting global climate and weather conditions. As scientific research continues revealing new complexities associated with El Niño phenomena and their relationships with climate change, more precise forecasting models will emerge. Satellite technology and climate modeling advances already provide valuable predictions, helping prepare for El Niño events. Preparation strategies include strategic water resource management, agricultural methodology adaptations, and natural disaster risk reduction, ultimately contributing to global efforts for adapting to changing climate conditions. Indeed, our understanding of Earth's delicate climate system balance emphasizes our collective responsibility for preserving this equilibrium for future generations. Exploring Earth's deep interior structure. For travel and adventure enthusiasts, descending into Earth's depths might seem rather mundane. Most of the interior consists of solid rock displaying gray, green, and red coloration, depending on dominant chemical elements. Earth's interior lacks fantastic caverns with dwarves, gigantic worms, or abandoned cities buried within continental depths. Extreme temperatures and enormous pressures prevent the fantastical subterranean landscapes once imagined by authors like Jules Verne from existing. Nevertheless, cutting-edge technology enables the underground world to impress us still. From oceanic floors to ancient chambers of Earth's history, we'll descend into our planet's depths and reveal secrets lying beneath, utilizing the most current available data. Our investigation employs an extensive array of Earth interior study methods. First, seismic surveys measure vibrations caused by earthquakes or artificially generated sources. Second, gravimetric surveys measure gravitational force distributions. Third, drilling operations extract samples from deep crustal boreholes. Fourth, paleomagnetic methods study magnetized crystal orientations in rock layers. Fifth, astronomical and cosmic approaches analyze meteorite samples. Sixth, laboratory methods reproduce and study geological processes through modeling. Finally, paleontological surveys examine ancient fossilized remains of animals, plants, and mollusks. This represents an impressive methodological arsenal. Therefore, we gather our equipment and begin our journey. The most straightforward approach to accessing planetary depths involves utilizing existing boreholes, which exist in considerable numbers on Earth. However, the deepest remains the Kola superdeep borehole, reaching 12,262 meters depth. No deeper penetration has been achieved. While this represents an impressively deep borehole, it remains surprisingly shallow compared to planetary dimensions. In total, this drilling penetrates approximately one-third of Earth's crustal thickness, representing merely 0.2% of the total distance to Earth's center. What discoveries emerged from the Kola superdeep borehole investigation? Initially, researchers recognized the need to revise temperature maps for Earth's interior, encountering temperatures far exceeding expectations. At 5-kilometer depth, temperatures exceeded 70 degrees Celsius. At 7 kilometers, temperatures reached 120 degrees Celsius. The 7-kilometer mark revealed one major discovery: the granite-to-basalt transition boundary. Another significant finding involved liquid water occurring at much greater depths than previously anticipated. One unexpected result was the discovery of open fractures filled with saline water, demonstrating that Earth's crust isn't solid. Pathways actually exist allowing fluid flow. Even more remarkable was biological activity discovery in rock formations. At approximately 8-kilometer depth, researchers extracted subterranean marine sediment layers preserving 24 ancient plankton species over 2 billion years old. Organic compound shells preserved these microorganisms virtually intact despite extreme pressure and temperature conditions in surrounding rocks. These fossils represent some of Earth's most ancient life evidence. Remarkably, Earth's deep interior actually hosts 1,000 trillion living organisms, many unknown to science. Record depths for subsurface sample collection reached approximately 5 kilometers below land surfaces and 10.5 kilometers below ocean floors. Moreover, up to 70% of all terrestrial microbial species inhabit underground environments. Several predominant types have been discovered beneath all continents. How these microbes spread throughout Earth's interior across all 5 continents remains unclear. They possibly migrate within deep zones or penetrate from surfaces through geological formation fractures. These results suggest that even on our planet, enormous masses of subsurface organisms could exist without noticeable surface manifestations. This indicates substantial grounds for not excluding life's existence on virtually any solar system celestial body, especially terrestrial planets. Having examined ancient Earth creatures, we continue rapid drilling. Before us lies the mantle, a thick layer of hot solid rock between Earth's crust and the molten iron core, composed primarily of silicates representing diverse compounds sharing common silicon and oxygen structures. Common mantle silicates include garnet and pyroxene. Another major rock type found in the mantle is magnesium oxide. Mantle temperatures vary dramatically, from approximately 1,000 degrees Celsius at the crustal boundary to 3,700 degrees Celsius at the core boundary. Therefore, we won't encounter any Tolkien-esque creatures. Viscosity also varies considerably. Primarily solid rock, but at tectonic plate boundaries, mantle rocks become soft and capable of plastic movement over millions of years under great depth and pressure. Heat and material transport within the mantle helps shape Earth's landscape. Mantle activity drives plate tectonics, contributing to volcanic and earthquake formation. The mantle divides into several layers: upper mantle, transition zone, lower mantle, and D-zone, the region where mantle meets outer core. The upper mantle extends from the crust to approximately 410 kilometers depth, remaining primarily solid, but with more malleable sections contributing to tectonic activity. The mantle transition zone exists at 410 to 660 kilometers below Earth's surface, where rocks undergo radical transformations. Rather than melting or decomposing, their crystalline structures experience significant changes, making rocks much denser. Perhaps the most important transition zone aspect is water abundance. Surprisingly, transition zone crystals contain as much water as all surface oceans combined. However, transition zone water differs from our understanding. It's neither liquid nor vapor. Instead, water exists as hydroxide, negatively charged hydrogen and oxygen ions, making tea brewing impossible. Incidentally, the mantle has never been directly explored, but many geologists study it by analyzing xenoliths, rock types enclosed within other rocks. Xenoliths providing the most mantle information are diamonds. Indeed, underground exploration becomes more appealing now, in a positive sense, naturally. Diamonds form under unique upper mantle conditions at depths of at least 150 kilometers below the surface. At greater depths and pressures, carbon crystallizes as graphite. Yet deep excavation may prove unnecessary, since diamonds sometimes rise to the surface during explosive volcanic eruptions, forming diamond pipes that can be mined for months. These enable examination of depths up to 700 kilometers below Earth's surface into the lower mantle. Research indicates that deep mantle rocks are most likely seafloor plates approximately 3 billion years old. Meanwhile, we reach the planetary core, Earth's extremely hot and dense center. This spherical formation exists at approximately 2,900 kilometers below the surface, with a radius of roughly 3,500 kilometers. Primary core heat sources include radioactive element decay, residual heat from planetary formation, and heat released during outer core liquid solidification near its inner core boundary. Precious metals including gold, platinum, cobalt, and others also occur in the core. While tempting, remember that an extremely hot journey awaits us. Another key core element is sulfur. Actually, 90% of Earth's sulfur resides in the core. Although we know the core represents our planet's hottest region, determining exact temperatures proves difficult. Core temperature fluctuations depend on pressure, Earth's rotation, and core elemental composition. Overall, temperatures range from approximately 4,400 to 6,000 degrees Celsius. The inner core rotates differently than the rest of the planet, spinning eastward like the surface, but slightly faster, completing an additional revolution approximately every 1,000 years. As Earth slowly cools, the inner core grows by roughly 1 millimeter annually through liquid outer core solidification or crystallization. Inner core growth occurs unevenly in segments, influenced by mantle activity. Growth concentrates around subduction zones where tectonic plates carry lithosphere into the mantle thousands of kilometers above the core. Plates extract core heat and cool surrounding areas, increasing solidification occurrences. The crystallization process proceeds very slowly, with constant radioactive decay in Earth's interior slowing it further. Complete core solidification would require approximately 91 billion years. Many geologists describe the outer core as Earth's geodynamo. For planetary geodynamo operation, rotation is required along with interior liquid medium. The liquid must conduct electricity and possess internal energy sources, driving liquid convection. Rotation, conductivity, and heat variations affect geodynamo magnetic field characteristics. Earth represents the optimal middle ground among solar system planets, rotating stably at 1,675 kilometers per hour at the equator, generating spiral convection currents. Liquid iron in the outer core excellently conducts electricity, creating electric currents that drive magnetic field formation. Energy driving outer core convection derives from liquid iron drops freezing onto the solid inner core. Solidification releases thermal energy as warmer liquids rise spirally upward while colder solid materials descend under intense pressure, creating convection. Our expedition concludes here. Hopefully, it proved enlightening. We collect our equipment and return to the surface. Indeed, our planet stands unique in its natural wealth, biological diversity, vast oceans, continents, and stable climate. Its interior plays crucial roles in planetary life evolution. Earth science knowledge enables global thinking and local action, discovering valuable resources like water, metals, industrial minerals, and energy, predicting and preparing for natural disasters, and studying our own planet more thoroughly than any other in the solar system. Alternative evolutionary scenarios for dinosaur survival. Examining this evolutionary history in detail, encountering remarkably diverse conditions and constantly shifting climate patterns, we can conclude that dinosaurs survived exceptionally well for over 160 million years, demonstrating enormous adaptive potential. If we hypothesize dinosaur survival, what factors might have influenced their continued development? The first major obstacle would have been climate change events, such as the well-documented Paleocene-Eocene thermal maximum, a geological event occurring approximately 55 million years ago, characterized by dramatic Earth climate warming, significant atmospheric composition changes, and various species extinctions. Global temperatures then rose 8 degrees above current levels, with tropical forests covering most of the planet. In this tropical world abundant with vegetation, it's quite possible that sauropods, among the largest herbivorous dinosaurs with elongated necks, would have developed more rapidly and reproduced at earlier ages, enabling faster population growth. A significant feature of the late Cretaceous period was the emergence of flowering plants or angiosperms. While Jurassic period vegetation consisted mainly of ferns and gymnosperms, which are generally less nutritious and more difficult to digest, the enormous size of sauropods likely resulted from the processing time and gut size necessary for efficient digestion of such food. If plant evolution had continued as in our modern world, herbivorous dinosaurs would almost certainly have developed diets based on flowering plants, which would have been easier for dinosaurs to digest. We might expect general body size reduction, with giant Mesozoic dinosaurs most likely disappearing. Another vast realm involves aquatic dinosaurs. After all, creatures like Spinosaurus were associated with aquatic environments, and armored ankylosaurs were often found fossilized in marine sediments or lived along coastlines. Could Spinosaurs or ankylosaurs have followed the evolutionary path of mammalian whales, completely transitioning to marine and oceanic life? Most likely, yes. Furthermore, they could have returned to land for egg-laying, or young could have been born at sea like ichthyosaurs and plesiosaurs. Marine dinosaur diversity would have created numerous terrifying legends while possibly leading to Lovecraft's emergence several centuries earlier. Regardless, if they had managed to survive to our era, selecting swimming locations would have required considerable caution, and warnings about not swimming beyond buoys would have been more relevant than ever. Although we shouldn't forget that no buoys would help in survival scenarios. By the late Cretaceous period, numerous bird species already existed. Unable to withstand competition, pterosaur diversity decreased during this time, leaving only massive, fortunately toothless asdarchids, some with 12-meter wingspans. Perhaps humans would have appeared as amusing toys to them, occasionally subject to involuntary play sessions. Researchers and paleontologists believe mammalian lineages were already developing before the extinction event, having to cope with small, dangerous animals like saber-toothed tigers and large antelopes. These creatures had to deal with various predatory dinosaur types, dromaeosaurids and abelisaurids. However, we shouldn't imagine a dinosaur world as constant bloody survival battles. After all, most predators are widely distributed geographically, making the world relatively safe. If humans had ultimately won this evolutionary race, even if it required much longer, some dinosaurs would have been domesticated. Others, particularly large predators or those with beautiful feathers, would have been exterminated. After all, humans historically exterminated many mammoths, Rodriguez solitaires, dodo birds, and other megafauna. Others would have ended up in reserves, while still others would have settled near humans like pigeons or rats. Other aspects of human life would also have changed. For example, since reptiles don't produce milk, it wouldn't be available in supermarkets, making milk-based products much less common. Culture would also have transformed from fashion to comic book heroes. Instead of Spider-Man, today's world would know Tyrannosaurus Man. Ancient Egyptian gods would have had heads of saurolophuses and, for example, hadrosaurids. Some consequences are difficult to imagine, providing much material for speculation. On this alternative timeline, perhaps some large herbivorous sauropod species, like enormous diplodocuses and even carnivorous ones similar to tyrannosaurids, could exist in protected deserts and national parks or reserves suitable for their life. These would have to be truly wild places, distant from humans, for example, in Australia or Alaska. Humans would most likely be able to go on safaris similar to Jurassic Park, holding binoculars and cameras ready to capture dinosaurs that had survived this entire long evolutionary journey. The smallest non-avian dinosaurs would perhaps easily adapt to urban environments and thrive alongside humans in cities, together with pigeons, rats, and seagulls. Small omnivorous or predatory theropods would perhaps hide around garbage containers and run about vindictively. Or imagine small herbivorous dinosaurs munching roses in your garden. What are your thoughts on this? Could dinosaurs have become intelligent? Could we coexist together on planet Earth? The Silurian Hypothesis, Ancient Civilizations and Geological Evidence. The introduction has already raised numerous questions. If answers exist for them, let's attempt to address them today. As you've understood from this discussion's title, our focus will be the Silurian Hypothesis. Essentially, this represents a thought experiment evaluating modern science's capability to detect evidence of previously existing highly developed civilizations, possibly several million years ago. Although this might seem like an absurd concept, more characteristic of conspiracy theorists, telepaths, and enthusiasts of various conspiracies like pyramid rockets, this thought experiment nevertheless occupies the center of attention in one scientific article whose author is astrophysicist Adam Frank. In his publication, he presented an advanced industrial civilization and pondered whether it could be detected in space in other systems similar to ours. Alternatively, we might prefer not to consider this, but what traces does modern human civilization leave behind, and how might proof of our existence be discovered in the distant future? The hypothesis is named Silurian, encompassing all supposedly former civilizations from archaic aliens to Atlantis. Some versions of the Silurian hypothesis suggest that a previous race completely died out due to some disease, war, or catastrophe. Another version indicates that the previous race achieved high technological levels and for some reason departed Earth to explore cosmic space, seeking new habitation. The most exotic version of the Silurian hypothesis is the involution hypothesis, according to which all animals descended from degraded representatives of races similar to humans. Yes, this sounds offensive. But let's return to genuine research. Considerable time and effort has been devoted to searching for climate change indicators on distant Earth-type planets, so-called hyperthermia, a type of rapid temperature increase that could indicate a civilization's industrialization moment. This might suggest the presence of a sufficiently developed species. Such a spike, possibly resulting from carbon emissions, may represent the only evidence that any race, including ours, will leave behind. Not pyramids, not skyscrapers, not plastics or foam materials, not Shakespeare's works, not Beethoven's music will indicate our presence in the past if we're discussing hundreds of thousands or even millions of years. Ultimately, we'll only be recognized by rock layer changes that marked the beginning of the so-called Anthropocene. This terminology is used by many researchers and signifies the current geological epoch when human activity exerts primary influence on climate and environment. Although the Anthropocene isn't yet officially classified as a separate geological epoch, it's already clear that humans significantly impact our planet's geological record, shaping it today. We're already a geophysical force, and our presence is recorded in carbon, oxygen, and nitrogen isotopes, in extinction events, various sediment deposits, heavy metal emissions, and synthetic chemical releases. For example, human fossil fuel combustion already affects geological data, despite industrialization beginning merely about 300 years ago. Well, with considerable stretch, this might be considered at least some advantage. We've managed to create our mark, yes, gentlemen. Future civilizations reaching certain development levels will be able to learn about our existence by studying ancient rock formations. So, let's imagine that perhaps some other species on Earth briefly rose to at least our development level millions of years ago. Do any traces of them remain today? For example, fossils, building remains, or space structure remnants? Possibly, but it may also be that all such evidence has been erased to dust, with only remaining traces existing in very minor geochemical features. Furthermore, fossils are extremely rare and fragmentary, so evidence could easily be overlooked, especially if the civilization existed for only a few thousand years, like ours. The truth is that modern humans have existed for a relatively short time, while life on Earth has existed by general estimates for 3.5 billion years. That is, Earth's history contained more than sufficient time for the rise and fall of not one, but several pre-human industrial civilizations. This could have been some race with its own technologies, transportation systems, folklore, and traditions, in the same location and under the familiar sky. But about such vanished civilizations, the industrial objects they constructed, existing no more than several 100,000 years, we have no reliable mentions, and not even one flying saucer with a mummified alien inside. We discover only the most ancient structures and tools created by humans, and these findings are merely a few thousand years old. Regardless, within several million years, when plate tectonics mechanisms activate, everything on the surface, including the land itself, will end up at the bottom of seas and oceans, while other areas will transform into mountain peaks. Speaking of our planet's age, it possesses quite considerable antiquity, and its solid surface, comprising land masses in different locations, varies greatly in age. Some of these land masses formed billions of years ago, while others formed from molten magma during the past 100 million years. Iceland, for example, began forming through volcanic activity only 70 million years ago, and some small islands continue forming today. From a geological perspective, one of Earth's most ancient locations is the Pilbara, a large region in northwestern Australia. Local rock formations first began developing more than 3 billion years ago. Its iron-rich stone segments serve as the best-preserved examples of the world's most ancient rock formations. Such ancient stones should be sources of quite interesting fossils. Generally, many desert regions where tectonic activity is absent and undisturbed rocks of appropriate age can be found are suitable for investigation. Who knows, if we grant the Silurian Hypothesis legitimacy, perhaps research will advance so far that with proper tests and investigations, someone will one day be able to confidently state, here was a human, Or perhaps a levitating humanoid with a large brain. That is, some civilization millions of years ago. Questions regarding planetary impact of civilizations may, incidentally, be significant for future research of other planets and our search for intelligent extraterrestrial life. Early Mars or early Venus were possibly more suitable for life than currently, and maybe one day we'll find those very geological deposits there indicating a once existing civilization. And yes, hypothetically, it's not excluded that previous Earth civilizations could have ventured into space and left artifacts on other celestial bodies, such as the Moon or Mars. Finding obvious material evidence in these two worlds will be easier than on Earth, where erosion and tectonic activity have erased most cultural traces. But still, why search for alien life there on other planets when we could find it here, removed not by kilometers, but by years? Indeed, several unexplained temperature anomalies are recorded in Earth's history that possibly could have accelerated the process of intelligent life's expulsion from the planet, or its death. For example, it's believed that 55 million years ago there occurred a sharp temperature spike known as the Paleocene-Eocene thermal maximum, one of the most significant and abrupt climate changes in geological history, lasting about 200,000 years. It manifested in severe temperature increases on continental surfaces and upper oceanic layers, as well as changes in atmospheric carbon isotopic composition and extinction of an entire series of species. According to climate reconstructions, continental temperatures at that time increased by 8 degrees Celsius. Water temperature in the tropical zone reached 20 degrees, which is 1.5 degrees more than the modern value. In Arctic seas, warming was significantly more massive, and the temperature increase of Arctic Ocean surface waters could have been up to 10 degrees Celsius. The thermal maximum manifested most clearly in the isotopic composition of carbon in carbonate sediments. During the thermal maximum, atmospheric carbon dioxide content reached at least 5 times more than the modern value. Moreover, most of it dissolved in oceanic water, thereby increasing its acidity. As a result, carbonate shells of dying plankton began dissolving in water. The thermal maximum could have been caused by an asteroid or comet impact, or it could have been a huge volcanic eruption, or it could also have been caused by the activity of an ancient civilization that rose like us and then fell. This, incidentally, may be the fate of all advanced species, rise and fall occurring as naturally as seasonal changes. Such a universe is ironic, constantly creating characters whose technologies lead to the very end they try to avoid. So the question, will we today be able to notice and identify traces of an early civilization's existence through archaeology and paleontology methods? And how can we accomplish this? This question remains open. One of the key questions in assessing the probability of detecting such a civilization is understanding how often industrially developed civilizations appear, given that life originated and some species became intelligent. There's little point in searching for buildings or long-lasting information carriers, since over millions of years tectonics and weathering will destroy them, not to mention the relative rarity of such structures on Earth. Today, for example, massive accumulations of durable constructions of human civilization occupy less than 1% of land area. That is, essentially, if a huge asteroid changes our planet's appearance beyond recognition in the near future, including human faces, considerable time will have to be spent to find any evidence of past life. And most likely, cave paintings in the style of "I was here" will hardly help identify our civilization. But even if not now, it's quite possible we'll disappear in a few centuries or millennia, essentially in an instant on the scale of geological history of the planet, and even more so of the universe. And then human civilization is just a small episode analogous to those that already took place in earlier geological epochs. And then in tens of millions of years, the next civilization will appear. Then another. Perhaps some civilization will still manage to become something greater, or maybe we are that very civilization, and we have every chance to go further, exploring and understanding ourselves, our planet, and other worlds. Looking at the cycles of rise and fall that seem to characterize planetary development, we must consider whether this pattern represents an inevitable aspect of intelligent life evolution. The geological record suggests that major environmental disruptions occur with surprising regularity, each potentially capable of ending civilizations before they achieve true permanence. Current evidence indicates that technological civilizations face a crucial test: whether they can develop sustainable practices before their industrial activities trigger irreversible environmental changes. The Anthropocene epoch we're creating may serve as either humanity's signature achievement or its epitaph, depending on our ability to recognize and address the consequences of our planetary influence. The search for ancient civilizations on Earth thus becomes more than academic curiosity. It represents an attempt to understand the fundamental challenges facing any species that achieves technological sophistication. If we can identify the markers of past civilizations, we might better understand both our own trajectory and what to look for when searching for life on other worlds. Whether examining deep ocean sediments, analyzing isotopic compositions in ancient rocks, or studying patterns of extinction and environmental change, each piece of evidence contributes to our understanding of how civilizations interact with planetary systems. The Silurian Hypothesis reminds us that Earth's long history could conceal the rise and fall of multiple technological societies, each leaving only the faintest traces in the geological record. This perspective fundamentally alters how we view our place in Earth's history. Rather than being the first and only technological civilization our planet has produced, we might represent just the latest attempt by terrestrial intelligence to achieve lasting success. The stakes of this realization extend beyond academic interest to encompass the very survival of human civilization and our responsibility to avoid repeating whatever mistakes may have led to the disappearance of our potential predecessors. As we develop better methods for detecting the subtle signatures that advanced civilizations leave in planetary geology, we simultaneously improve our ability to monitor our own impact and potentially course-correct before we become merely another brief anomaly in Earth's vast geological record. The search for ancient Earth civilizations thus becomes inseparable from the quest to ensure our own civilization's longevity and success. Thank you for watching this video. If you liked it, give it a like and don't forget to subscribe to the channel. Thank you and see you in the next videos. Take care.